Good day, everyone. This is Tutor David right here, and this is Academy X again coming to you with a tutorial on PCH 231, which is Pharmaceutical Inorganic Chemistry. And today we are going to be focusing on chemical and ionic equilibria in details, explaining everything to the barest minimum as a pharmacy student that you should be able to capture. And we're going to be covering everything about chemical and ionic equilibria as it relates to this particular course. Do well to pay very close attention to all that will be discussed because indeed it's going to be vital to help you to ace in this particular course. All right, so this chemical and ionic equilibria, it's actually such that we need to understand the equilibrium that occurs in terms of chemical structures, chemical relationship, chemical formulas, and then as well as the ionic aspect of it is going to impact how drugs actually get to be distributed in the body. And now look at the first statement that we have here. It is the statement that acid-base properties of a drug can influence its biodistribution and partitioning characteristics. This is actually very important because it decides or it informs how the drugs get to be distributed in the body. As you go on in pharmacy school, you get learn about pharmacokinetics, where you understand what the drugs do to what the body do to the drugs. That's what I'm trying to talk about. So you have things like absorption, metabolism, distribution, metabolism, and then excretion. That is ADME. All right. So and then you need to understand that drugs basically have acidic or basic functional groups, and by implication, any drug you get to see will most likely either be acidic acidic or weakly basic. So drugs generally are weakly acidic or weakly basic. So depending on whether they are acidic or basic is going to inform or impact on their absorption characteristics. So the first thing we're going to do is we're going to look at examples of acidic drugs. We're going to look at examples of basic drugs, and from there we're going to make progress to talk about theories of acid and base reaction. So let's now move on. So there are acidic drugs. Acidic drugs happen to have some acidic functional groups that are predominant in those drugs that confer on it those acidic properties. When we look at theories of acid and base, we'll get to understand how you can identify acidic functional groups, and then you can be able to identify how to identify basic functional groups. So drugs with carboxylic acid is the first class of acidic drugs we're looking at. Drugs with carboxylic acid. All right, so before you make progress from here, I want you to make sure that you have gone through the basics of aromatic chemistry, organic chemistry, where you get to understand how to identify functional groups. So for carboxylic acid group, just if you go to Google, just type functional groups, you get to see a lot of images that show you different functional groups, so you can go to familiarize yourself with them. So let us look at carboxylic acid group. So carboxylic acid group is written as COOH. Now, in form of structure, this is going to appear as C double bonded to oxygen, single bonded to OH. So anytime you find a group that has carbon double bonded to oxygen and single bonded to OH, that particular group is known as carboxylic functional group. You could also find this thing written like this. So you can find something like this. All right, so in chemistry, when you have any spots like this, what is actually there is carbon. So this is something as this, and this is something as this. So what you have there is carbon, and then you can have any aryl or alkyl group attached that way. So but what we're interested in is the functional group, which is carboxylic acid. So drugs with carboxylic acids tend to display acidic properties. So we're going to be looking at all of these drugs, and we're going to be looking at the functional groups, and then we'll now identify the carboxylic acid group, which is responsible for the acidic properties that it possesses. All right, so the examples of the drugs we have here, we have warfarin, we have aspirin, we have methotrexate, and we have furosemide. These are examples of drugs that have carboxylic acid groups, and they are acidic drugs as well. All right, so the first one we are going to be looking at here is going to be the aspirin. So what we're going to be looking at here is going to be aspirin. So this structure is the structure for aspirin. Now, another name for aspirin is also known as acetyl salicylic acid. All right. So aspirin is also known as acetyl salicylic acid. The reason why I said acetyl salicylic acid is that this is an salicylic group here. So before the addition of the acetyl aspect of it, it is acetyl salicylic acid. The moment you add that acetyl aspect, it now becomes acetyl salicylic acid. So, but then the common name we have is aspirin. So let's look at the functional groups we have in aspirin. So in aspirin, looking at the aromatic group here, we have carbon double bonded to carbon. Yes, double carbon double bonded to carbon. So that is going to be like C double bonded to C. But in this context, it is an aromatic bond. It's in an aromatic structure. So this is aromatic in nature. This is aromatic in nature. For example, let's look at this. All right, so let's let's look at this. This should be two. Yeah, this should be two. All right, so what we have here, this is called 18. So this is also a functional group you have, like it's an alkene functional group where carbon is double bonded to carbon. But in this case, this carbon double bonded to carbon um, is aliphatic. All right, so it's aliphatic, so it is not aromatic. So when you start talking about C double bonded to carbon in a ring system, that is an aromatic, C double bond to C functional group. All right, so the next functional group we are going to be looking at here, we're going to be looking at this functional group. So yeah, you should be able to tell what this functional group is right now. So that is the carboxylic acid functional group. So that is our COOH. So what you have here is the carboxylic acid functional group. We have already discussed about that prior to this time, the carboxylic acid functional group. All right, so in this particular context, what we have here is an ester group. So let me show you what an ester is like. So if you browse and check out the functional groups you have, ester group will most likely be represented as COOR. So ester group will most likely be represented as COOR. Now this COOR in terms of structure is going to be something like C double bonded to O, and then R. R can be an aryl group or alkyl group, like just any carbon chain from there. So if you want to now represent it using this kind of stuff we have here, so it's now going to be this double bond to oxygen, and then you now have your O, and then you have your R. So this is double bond. So I can clear to you, this is double bond here, double bonded to O, and then you have single bond to this, and then you have OR. So let's now come back to this place and let's see what it is like. So you can see this is the C point, the C is double bonded to O, single bonded to O. The arrow in this case is now this compound. So this is the arrow in this case. Like I told you, arrow can be aryl group or alkyl group. What is aryl group? Aryl group refers to like ring systems like this that is lacking in one hydrogen, while when it comes to alkyl group, it's also a similar situation, but it's straight chain compound, aliphatic compounds that is lacking in one hydrogen, and then that's now helps in the bond. All right, so what we have here is an ester group. So what we have here is ester group. So you should be able to draw these groups in the events that probably maybe your lecturer decides to ask you what groups are present in aspirin. You can simply tell him, first of all, we have C double bonded to C aromatic group. We have the carboxylic acid group, which is COOH, and we have the ester group, which is COOR, and that you get your mark for that. So what is responsible for the acidic property of aspirin is the carboxylic acid. All right, so let's now make progress to the next one. So this particular structure we have here is the structure for furosemide. So this is furosemide. Meanwhile, it will interest you to know that aspirin is a medication that is classified under the non-steroidal anti-inflammatory drugs, which is usually labeled as NSAIDs. So yeah, this is non-steroidal anti-inflammatory drugs. So NSAIDs are anti-inflammatory drugs and analgesics, so they help to prevent or slow down inflammations as well as relieve pain. So it's like a painkiller basically. So aspirin is a painkiller. It's an analgesic. It helps to relieve pain, relieve inflammations. So, but it also has other uses. It can also be used for thinning of blood. But as you go on in pharmacy school, you get to learn more about aspirin. So, but for furosemide happens to be a diuretic. What's a diuretic? Diuretics are drugs that causes one to urinate more frequently. That is diuresis. So the drug is diuretic, which induces diuresis. Diuresis is like frequent urination, like increased urination. So that's what furosemide does. And the reason for that, there are different reasons for which you want to administer furosemide. One of them is when there's a case of high blood pressure, which is a function of several factors, including high volume of fluid in the body. So, but then that is not our focus. Our focus is why is furosemide classified as an acidic drug? Is because it has carboxylic acid group. So let us now look at what we have here. You can already see that because we have a ring system here where there's a double bond, automatically we have the CC aromatic group in furosemide. Yeah, we have the chlorine attached to it. Yes, so that is the chlorine. Then we have an amine group here. So this amine group, let me show you what amine group is. So amine group is wherever you have NH3. This is an amine group. So, but the thing about the amine group is that the amine group can be primary, it can be secondary, it can be tertiary. So it can be primary, secondary, and tertiary. All right. So this one right here where you have the nitrogen, just sorry, this is not 3, this has to be 2. Nitrogen can only accommodate 3 bondings. Nitrogen can only accommodate 3 bondings. So if you want to put this in terms of structure, it's going to be N H H. So nitrogen can only accommodate 3 bondings. So it has 1 bond to whatever carbon or whatever, and then it has 2 hydrogen. This is primary amine. Then if you now talk about secondary amine, you have the nitrogen attached to 2 different carbons. So in secondary amine, you're going to have the nitrogen bonded to let's say 1 carbon here, maybe another carbon here, or probably you could say another carbon here, and then you just have 1 hydrogen left. So this is a secondary amine. Sometimes it can be represented as N uh, let me clean this. You can see very clearly. All right, so this is so sometimes please pardon me for this error. All right, so sometimes you can represent it as N and then just H out together now. So this is the same thing. This is a secondary amine where you have the nitrogen bonded to 2 different carbons, while in primary amine it's only bonded to 1 carbon. Tertiary amine, you have the nitrogen bonded to 3 carbons. So in that case, you now have something like N, and then there is no hydrogen attached to it. So this is primary, this is secondary, and this is tertiary. So coming over to furosemide, this one you can already know what it is, right? This is a secondary amine. So this is secondary amine group. Now the amine functional group or amino group gets to confer basic properties on the drugs, but this is not a base. The reason I'm going to explain to you later. All right, so then the what you have here, this is a furan ring, is not contributing probably like any significant basic or acidic properties. So this is furan ring. Then yeah, this is a sulfonyl group. This is a sulfonyl group. It has some level of acidity attached to it. And then this is another amine group. This is another amine group. But then in this case, why this is secondary, this one is primary amine. So secondary amine, you can secondary amine can be represented as 2 with a degree attached to it, while primary amine can be written as 1 with a degree attached to it. Meanwhile, tertiary amine is written as 3 with a degree attached to it. So anywhere you see maybe 1, 2, or 3, it tells you the kind of amine you have there. So but then our most useful or vital compound in terms for classifying this as an acidic drug is our carboxylic acid group. So this is our COOH. So the carboxylic acid group is the effect is much stronger than what you have from the secondary and the primary amine, and as a result furosemide is classified as an acidic drug. And then the last acidic drug we'll be considering today is going to be the warfarin. So is going to be the warfarin. Alright, so warfarin is an acidic drug. It's usually used as an anticoagulant, used to make the blood much more thinner. Yeah, and for several other purposes. So what are the functional groups we have in warfarin? So in warfarin here, you can find the C double bonded to C aromatic group in the ring system. All right, then you can have the OH. This OH is referred to as phenolic phenolic group or phenolic OH group, phenolic group or phenolic OH group. Once OH is attached to an aromatic compound, it is referred to as a phenolic OH or phenolic group. So, but in the event that OH on its own without having any of the acidic kind of stuff is attached to like an aliphatic compound, it will be referred to as like an alcoholic OH group. Alright, so as you go on in chemistry, you get to understand those things more better. Alright, then you have the O as an heteroatom in the cyclic group. Then here you have C double bonded to O in the heteroatom, here also in the aromatic ring. Then in this particular place you have the C double bonded to O, and then uh, you have the bonds still continuing. You have the bonds still continuing, and this does not have so much impact on the structure. Then on this particular aspect, you have like the normal regular, you have the normal regular ring that is available there. You have the normal regular ring that is available there. All right, so just for the purpose of context, this particular warfarin, I think that is somewhat of an error from my own end. This particular warfarin is supposed to be under the phenolic group. Please just take note of that. Warfarin is supposed to be under the phenolic group because the group that is relevant for warfarin to be considered as an acidic group is not carboxylic. Like if you look around here, you will not find like any carboxylic group here. What you are going to find is a phenolic group. So let's now go down to the phenolic and you start with warfarin for the explanation. So drugs with phenolic group are also classified as acidic drugs. So we have paracetamol, we have morphine, we have levothyroxine, and like I've already told you, we also have warfarin. So the phenolic group here, the OH, the H here can be donated. And when we look at the theories of acid and base, you understand what I mean by donated. When it is donated, it means that it has acidic properties. So by implication, this is what makes warfarin to be acidic because of the presence of the phenolic OH group. Then when we now come over to this, what we have here is paracetamol. What we have here is paracetamol. Alright, so what we have here is paracetamol. So in the context of paracetamol, what we have for paracetamol, the reason why it's called para is because the two groups that are on the aromatic chain, are para to each other. The two groups on the aromatic chain are para to each other. So you have this. Now, in terms of chemistry, let me explain what all of those things are. So this is our ring structure. This is our ring structure. Is our ring structure. Then, for example, let's assume that there's a group here. Assumption. We can actually say let's have an OH here, for example. Now, when you have this, if there's an attachment of any group here, we simply say that this group is auto to this particular. So any attachment that is just one bond away on an aromatic ring in this form, we call it auto position. So this is referred to as auto position. Meanwhile, if this is not here, and then what you have is at this point, this particular position is referred to as meta position. This particular position is referred to as meta position. And then if what you have is not here, but you now have it here, for example, where that is like 1, 2, 3, 3 bonds away from the reference group you have on the aromatic ring, we refer to that position as para. So the question for you is, if something is attached there, what will it be called in reference to the OH? Very simple. That is going to be auto. If something is attached here, that's going to be meta. And something is attached here, that's going to be para. Another example for you, so that we can be able to see different ways it can be used, is that we can have something like this. we can have something like this. So for example, you have a compound here, for example OH, and for example you have NH2 here. This is a ring. Now it's still same principle. So this is 1, 2, 3. So this is the para position. So this is para to this. Automatically, that is what we're working with in paracetamol. So in paracetamol, this is auto, this is auto, this is meta, and this is para. So it is called paracetamol because the phenolic OH group is para to this amine group, which is like a secondary amine. So what we have here, we have a phenolic OH group in paracetamol. We have a secondary amine. We have a secondary amine group. But if you want to consider it like much more fully, if you want to consider it much more fully, this is more like an amide group. This is more like an amide group. So when we talk about amide comes in this form. So this is CONH. So it's going to be something like NH and then actually NH2, but then depending on what is connected to the N, if there are more bonds to the N, then it's considered like that. So this is going to be C double bonded to oxygen and then single bonded to N, and then you have the H. If you have something attached to it, for example, because many times there may be no attachment, but you have something attached to it, now this is secondary, but this is primary. So in this particular context, what we have here is an amide group. So this is an amide group generally. So even if this is like a secondary amine, generally when you look at it in the real context, this is an amide group. Amide group, not including this part. Now let me tell you something about organic chemistry. Whenever you see structures in organic chemistry that just end this way, for example, you have that here, there's nothing here, there is nothing here. Whenever you have such kind of structures, let it be known, for example, also here there's nothing here. This particular place, what you have there is a methyl group. Basically, it should be known to you. So in the event that you're asked to like draw a full structure or something, you should know what is there. And what is a methyl group? Methyl group is CH3. So the CH3 group is like the methyl group. So that is the methyl group that you have there. So CH3 group is what you have at this different portal. So what is important to us actually this group? Remember this is C, this is CONH. Are we making sense? So that is like our amide group. So amide group is para to the phenolic group, or you can say the amine is para to the phenolic group. You are still correct because this is like a secondary amine, and because they are para, that's why they call it paracetamol. Paracetamol is also known as acetaminophen. Paracetamol is also known as acetaminophen because of the acetyl group and the amino group, and then fen because this is like a phenol compound. QC chemistry is actually very, very interesting. I hope that makes sense to you. So this is an acetyl group, this is amine. When you add them together, that is amide, and then you now have a phenol, so they now call it fen, acetaminophen. So but paracetamol is like the popular name, and the mol is because like it has this phenolic OH group, making it look like an alcohol or something like that. All right, so that is basically it, and what confers the acidic properties on it is the OH group, just like the warfarin. So let's now go back to the basic drugs. So basic drugs, usually many of them will have the amino functional. There are other things that can be like visible in basic drugs. So, but one example we have is phenylbutazone. It has the amino functional group, and if you look at your resource material, the amino functional group there you have is a tertiary amine. It's a tertiary amine. That's what you have in phenylbutazone, but we're not drawing that here. What we're going to be focusing on is procaine. So for procaine, this is the structure of procaine. This is the structure of procaine. So in procaine, what are the functional groups we have here? We have an amino group or amine group. Yeah, it's an amine group, not necessarily amino. So this an amine group, and then the amine group we have here, this is a secondary amine. So that's a secondary amine. Then we have the C double bonded C aromatic group. Then in this particular context, we have the ester group. Yeah, we've already talked about ester. Yes, this is ester group. So that is COOR. So that is a COOR. So this is an ester group. So this particular one is like an ester group. Then this is like normal aliphatic group. Then this is N, but this time around this is also an amine, and this amine group is a tertiary amine. This is a tertiary amine, and then you have like your CH3, CH3. So what is conferring the basicity or the basic nature for procaine is the presence of amine group. You have the secondary amine and you have the tertiary amine. Ester group is not actually conferring so much. What is much important is this are these two amines are present in protein. So that's what make up basic drugs. So as we go further, we are going to be looking at the theories of acid and base. But before we go over to the theories of acid and base, there's something I need to let you know about drugs. Drugs are absorbed better in their unionized form. Do not forget this. If you forget every other thing we've done in this tutorial, of which you should not forget anyway, every one of them is very, very important. But do not forget this, that drugs are absorbed in their unionized form. Drugs are better absorbed in their own ionized form. And for drugs to remain unionized, they have to be in an environment that does not allow for ionization. So when acid drugs or when acidic drugs are in acidic environments. Alright, so when acidic drugs are in acidic environments, they remain unionized. When basic drugs are in basic environments, they remain unionized. But when you have acidic drugs in basic environments, they become ionized. And when you have basic drugs in acidic environments, they become ionized. So drugs are better absorbed in their own ionized form. And you need to understand that the stomach, the pH of the stomach is acidic, is such that it's acidic, while in the intestine, the pH is basic, but then the blood itself is around 7.4, and 7.4 is close to like the middle, yeah, which is almost neutral. So but that's slightly basic, yeah. So in the stomach you have acidic condition, in the you have basic condition. So you can be asked a question and you can be asked, paracetamol, where is paracetamol better absorbed? You know that paracetamol is acidic. Then the next question is, in the stomach we have acidic condition, in the intestine we have basic condition. If the paracetamol is acidic, where will it remain unionized? According to what we have there, it will remain unionized in acidic environments, which is consistent with the stomach. And if it is going to remain unionized in the stomach, it means that paracetamol will be better absorbed in the stomach region. I hope that makes sense to you. Then if you want to talk about procaine, for example, if procaine is taken via as like a tablet, for example, just for context, in that case you will need a basic environment for it to remain unionized, and in that context that would be the intestine. So that is basically that about that. So let's now move over to the theories of acid and base.